Ladies and gentlemen, a pleasant afternoon to you all. I'm here to share our research on the subject of auto-training with reinforcement learning for permissioned blockchain systems. My name is Dongnong Huo from Institute of Information Engineering, and it is with pleasure that I address you today. As we're aware, the advent of Turing-complete smart contracts have revolutionized permissioned blockchains to process nearly all types of transactions executable within a traditional database. However, current research holds a critical point that the conventional approach of improving performance through hardware upgrades, which is a mainstay of traditional distributed databases, does not yield comparative results for permissioned blockchains. Taking Hyperledger Fabric, one of the most popular blockchain systems, as an example. Thus, the demand for an optimization method is also imperative. In previous studies on parameter tuning, there's a trend to follow the idea of traditional distributed databases. Well, even the recent advance only trained a few parameters. And this is merely the tip of the iceberg for commercial blockchain instances with hundreds of parameters. In fact, large numbers of parameters make manual tuning methods troublesome even for experts. Therefore, auto-tuning methods are recognized as feasible solutions which have shown some outstanding approaches. However, directly applying the auto-tuning approach from distributed databases to optimize Fabric is still intricate for three challenges. First, using a recent database benchmark suite to remeasure Fabric is difficult for users, as Fabric schemes require collecting mixed responses from all nodes that execute transactions. Second, Fabric is less sensitive to the workload as dynamic configuration turners, and it also needs to pay attention to the consensus and verification process. Third, there is no previous knowledge to guide the selection of Fabric's important parameters. So, in this paper, we propose a novel scheme to auto-train parameters for Fabric, namely Athena. To be specific, Athena uses a centralized training with a decentralized execution method for the training process. Then it has an efficient reward function to shorten training time, and it filters out the most important configuration parameters to accelerate auto-training efficiency. To the best of our knowledge, Athena is the first auto-training system to optimize performance of Fabric. Here, we will introduce the system architecture. Athena contains four components. First is the client panel. It is responsible for receiving tuning requests from users to coordinate and control the operation of the entire system. The second is the information collection, where we leverage two benchmark suites to evaluate and record the performance and resource usage of the blockchain within current parameter configuration. Then all collected data will be sent to our innovative multi-agent DRL training process for parameter training across diverse node types. Then we employ lasso technique to identify crucial parameters that impact more of the performance to enhance the efficiency during turning. To leverage DRL, we should map the application signals to necessary components. First, the environment represents our training target. That is, an instance of Fabric in the article. This includes types of different nodes and the blockchain network architecture. Then, we use the agent to adjust the output strategy according to the state and reward. We design agents for peers and orders respectively, as they occupy most of the time for executing transactions. And they also design a separate agent to separate network-related parameters from the peer and order for better training. Third, the state space of the fabric is composed of all observations of participating nodes in the transaction observed by different types of agents. According to official documents of Fabric, we selected 37 internal metrics and 4 physical resource status information. Finally, we take the parameter of each node in the Fabric network as an action. By excluding some parameters that are not obviously related to performance, we selected 51 parameters as our action definition. Precision in defining a reward function holds utmost importance, as it directly shapes the outcomes of our model. Drawing inspiration from CDBT term, we tend to use an exponential reward function to amplify the significance of performance shifts. Besides, we also introduce a scaling factor to quantify performance changes. Based on the description above, we will introduce our DRL scheme. The traditional MADDPG algorithm requires all the agent state and action information as input when training the critic. Well, we further extended MADDPG and implemented an algorithm to fit the actual scenario of Fabric. This contains a two-part optimization. First, as nodes of the same time play similar roles, we divide the participating nodes into 3 groups. They are the peers, orders, and networks. The same type of node has the same configuration, thereby reducing the number of trained models and accelerating overall training. Second, we add a scheduler to the original MADDPG to further abstract the observations of all agents and calculate the average value of the observed node states separately according to their type. Formally, we define the ith node states in relation to internal metrics and physical resources, and get the state spaces for peers and orders and network. They together build Fabric state space S. Finally, we define the abstraction of nodes observed by all 3 agents to establish the abstraction of all agents' observations as A. The PB MADDPG algorithm is attached here. It contains the iteration process, the updating of actor and critic networks. For comprehensive understanding of the algorithm, please refer to the full paper. Moreover, we normalize the date to feature them with some order of magnitude, which can help us use lasso to rank the importance of the parameter. In our experiments, we use the following configurations as our experimental configurations. Further, we use the smart contract, simple and small bank with caliper benchmarks. They have been used as representative workloads in previous studies. Taking 3 network scale as the comparison, we start our test. First, Athena reduces the deployment time to under 1.5 minutes by automatically restarting Fabric. However, on average, the deployment time still accounts for 86% of the entire scheme. It's unavailable in any optimization scheme as we would wait for Fabric to take effort with new parameter configurations. Then we compare our scheme and reset approaches. We found that training time increases with the number of nodes, and expert manual training only addresses 4 parameters has significant limitations, where Athena's training solution scales well with the number of nodes. Further, we use lasso to rank the importance of the parameter and found that 20 parameter is the training sweet point. Thus, we argue that the training time can be significantly reduced if important parameters are identified. As Fabric supports users to dynamically join the network, Athena should fit for the scalability. As shown in the figure, the configuration recommended by Athena is adaptable. We also examined 2 crash situations and found that Athena can ensure consistent and high-performance usage of Fabric network during crashes. In conclusion, Athena is a Fabric-based auto-training system that can automatically provide parameters for optimal performance. It only requires the controller to have the privilege to modify the configuration and restart Fabric in the training stage. Then we describe the relationship between the parameters and performance and transform the problem of training parameters into a multi-agent coordination problem. Further, we propose a novel PB-MA-DTPG algorithm and select the parameters that make the greatest contribution to solve the training problem. At last, we found that the training recommendation from Athena is more effective than that of the default configuration, and our method outperforms the other 3 most advanced solutions. So, we are among the first to study auto-training for performance optimization of permissioned blockchains. That's all of the presentation. Thank you for your interest.